All right, aloha and welcome to my talk on leveraging macOS's network frameworks to heuristically detect Mac malware. We have the standard RSA disclaimer. I haven't read it. I'm assuming it's good. Let's dive in. So my name is Patrick Wardle. I am the founder of the Objective-C Foundation, also the author of the Art of Mac Malware Analysis book series, and most recently the co-founder of W, which is a startup designed to empower those building security tools for the enterprise. The idea is we build libraries, frameworks, modules that then can be integrated into other larger security products. Now, I like to start my talks by describing what we are going to learn about today. One of the reasons is if it's not interesting, you can just leave right now. So, in a nutshell, we're going to see how to leverage Apple's network frameworks to build network tools to detect malware. Part one of the talk, we are going to look at various Mac malware samples. This is going to give us an understanding of what Mac malware looks like, how it utilizes the network. We're then going to talk about how to build tools that can either give us a snapshot of the current network activity on a Mac, or then build a comprehensive network monitor that can give us information about network activity in real time. And then finally, with the ability to detect network activity on the host, we want to end the talk by determining if this traffic is unauthorized and if it is potentially associated with malware. Now, the idea, and this is not necessarily that novel or groundbreaking, is that we should be able to detect malware via its network activity. And this is based on, again, the rather obvious statement that malware is going to utilize the network. And so if we can detect this unauthorized network access, we should be able to uncover malware. And we will look at some examples of Mac malware. As I mentioned, we'll see it uses the network, for example, to create reverse shells, to propagate to other systems, to perhaps get tasking from remote command and control servers, download, exfiltrate files. A lot of network activity that, in theory, if we can detect this, should allow us to uncover this malware, even if perhaps other detection mechanisms fail. Now, normally, network monitoring is done at the network level. You're probably all very familiar with taking a network appliance, plugging it in somewhere into the enterprise network, and then configuring all the hosts so that their network traffic is routed through that box. And there's pros and cons to that, but there's also a lot of downsides to this approach. And the main downside, in my opinion, is, as we've seen recently, even though this is 2024, a large number of these network appliances have gnarly security vulnerabilities in that adversaries are attacking and utilizing and leveraging to get access into networks, which is, to me, is both very disappointing and also ironic, right? You plug in this network appliance that's supposed to increase the security. China, or your favorite adversary, finds 0-day, hacks in, and now the network is owned through the security device. Not ideal. So what we're going to be talking about today is instead doing the network monitoring on the host, on the actual endpoint. And I personally believe there's a ton of benefits to that. First and foremost, this allows us to identify the process responsible for the network activity, which is very, very important because if you're on a network appliance and you see some network traffic, how do you know what process, what program generated that? Is that Google's Chrome updater that's legitimate, or is it something masquerading as that? You don't know because you're not on the host. But as we'll see, using host-based approaches, we can comprehensively determine that. Also, this is all pre-encryption, so we don't have to man-in-the-middle network traffic to uncover network streams. That's really great. And also, you don't need any extra hardware. You don't have to go out, pony up all this extra money for a network appliance, which also might be how the adversaries get into your network in the first place. So host-based networking monitoring is great, but it's been a wild ride on macOS, which is one of the reasons I'm giving this talk today. Kind of show you the blood, sweat, and tears, but also show that we're in a lot better position than we were even a few years ago. So some recent examples. We're going to talk a lot about the Network Extension Framework. This is a framework you're going to use if you're building networking tools on macOS or iOS. Unfortunately, when Apple released it, it was very buggy, which means if your programs utilize this network, networking framework, systems might panic and everyone would blame you, even though your code was not buggy, Apple's was. So that was unfortunate. Good news is Apple has now patched this. A lot of the frameworks that exist on macOS and iOS that we want to utilize to build network monitoring tools are private, which means they're undocumented and we have to reverse engineer them. That's kind of annoying as well. And finally, Apple's documentation is often sorely lacking. Even worse, when Apple released this network extension framework, they neutered it without telling anybody. So via reverse engineering, we uncovered the fact that there was this exclusion list which contained a large list of system daemons, programs, and even applications that Apple had decided, okay, these applications, their network traffic should not be routed through the network extension framework. Well, this is very problematic because Apple also said, hey, if you're building a firewall or any network monitoring tool, please use this network extension framework. This is actually the essentially only supported way to do that. So you can imagine if there's a large number of daemons and applications whose traffic is not being routed through that, it leaves the firewall incredibly blind. It took me literally 10 seconds to find a way to leverage one of these trusted excluded programs to generate arbitrary network traffic on my behalf, allowing me to build a covert command and control mechanism that would bypass any firewall. The good news is, went to Apple, they said, yeah, this is kind of by design. Talked to some of my friends in the press, they made some news, and this is what got Apple to change their mind. So big takeaway here, if you want Apple to change something, they're not going to listen to you, they listen to the media. It's unfortunate, but is a reality. All right, so now let's look at some recent Mac malware samples, and as I mentioned, this is going to give us a good understanding of what generally malware does to utilize the network, which is the activities we want to detect. So the first sample is called Dummy. I named it Dummy because it's a fairly basic piece of Mac malware. You can see it's about 10 lines, 15 lines of code. It's basically some Python script that's embedded in a bash file that the adversaries would persistently install. And all it does is create a reverse shell. So even though I called it Dummy, it does give remote adversaries complete access over an infected system. So we can see it connects out to a remote server. It duplicates standard in, out, and error, ties those to the socket, and then spawns an interactive shell that's tied to the socket. So it's a vanilla reverse shell. Another sample we have is IP Storm. IP Storm uses the network in two ways. First, and most interestingly, it uses the network to propagate to other systems. This is not something we see very common in Mac malware. Most Mac malware, when it gets on a host, it doesn't try to spread autonomously. What IP Storm would do is it would try to brute force SSH accounts on other systems. So interesting, and again, network activity that if we're monitoring for might allow us to detect an infection. It also creates a reverse shell similar to Dummy. Next up, we have GoRat. GoRat is a standard macOS backdoor, fairly fully featured. You can see it has commands, for example, to download, upload files, create a screenshot, et cetera, et cetera. But it is interesting because it has several other commands that are specific to network type activity. For example, you could, from an infected host, give it a command to port scan another host. You could also set up a proxy, a tunnel, et cetera, et cetera. This was interesting because the adversaries were then able to use this to, say, infect one system on maybe the external facing side of an enterprise and set up a tunnel to then talk to other perhaps infected systems internally. Another interesting thing about GoRat, all its communications were multiplexed over one connection, which is kind of neat from the malware's point of view. Less network traffic, there's only going to be one connection at a time. Now, more generically, let's talk about supply chain attacks, because this is where network-based detections really shine. I'm sure we're all familiar with what supply chain attacks are. Let's look at a recent example. 3CX, a popular PDX software provider, was popped by the North Koreans. They were able then to access 3CX's build server, where they surreptitiously modified both the Windows and Mac OS installers. We're going to focus here on the Mac OS. What they did after they created this Trojanized installer, they signed it using 3CX's code signing certificate because they were in the network on the build server. And then, dishearteningly, the attacker sent it to Apple, and Apple notarized it, which basically means Apple scanned the Trojanized application, didn't find anything wrong, and gave it their stamp of approval. The reasons the adversaries did this is in order for software to run on recent versions of macOS, it has to be notarized. So then this was inadvertently deployed to users and enterprises around the world. Really no fault to them at all. They're getting this software from 3CX Official. It's been signed. It's been notarized by Apple. All is good, right? Unfortunately, no. And this is, again, one of the biggest problems with these supply chain attacks is not only the impact they potentially can have, but also how difficult they are to detect. So how was this 3CX attack discovered? Well, convenient for this conversation, via network traffic analysis. We can see that a certain IDS vendor picked up on the fact that the 3CX application was talking to a strange domain, specifically this msstorageboxes.com. So this attack was not detected by any signatures or other heuristics, merely by the fact that there was anomalous DNS traffic being generated. Other malware that's very difficult to attack and rather detect is malware that runs on iOS. Now, this presentation is mostly focused on macOS, but a lot of the code samples we're going to talk about, frameworks, also exist on iOS. So in theory, taking what we talk about today and applying it to iOS, at least in some capacity, is likely possible. So iOS software, malware rather, is very difficult to detect. On my macOS system, I can pop into a shell, see what processes are running. I could run security software. On iOS, I have no idea, right? So I'm a security software expert. I'm pretty sure my Mac is not hacked. I have no idea if my iOS device is hacked or not. Like, how would I do it? I mean, I could maybe dump some files, poke around. It's very, very, very difficult. And this is an unfortunate side effect because iOS is, yes, more secure than macOS. But what advanced adversaries do, three-letter agencies, your favorite nation-state governments, they have a lot of remote, or at least some remote iOS bugs. And once they get into your iOS device, they can use the security of that device to their gain, right? You can't even look at what is running on your iOS device, which again is good for basic security, but for the advanced adversaries, that's actually beneficial to them. So how do we detect malware on iOS? Well, other than looking at crash reports, which are few and far between, the answer is network activity. So case in point, Kaspersky got hacked recently. Their iOS devices were infected by a very sophisticated adversary who remained undetected for 4 years. And this should just drive home the point how difficult it is to detect malware on iOS. Kaspersky is arguably one of the best security companies in the world. And the fact that their systems remained detected for 4+ years illustrates that. Now, how was this ultimately detected by Kaspersky? Well, they noticed anomalous network activity. And that's how they were ultimately able to figure out that their devices had been popped. So now hopefully I've illustrated that Mac malware uses the network, obviously, but also that network-based detections are, in some cases, the best, if not only way to detect advanced adversaries. So let's look at some specific examples of code and approaches we can use to write security software to detect unauthorized network activity. And we're going to start by enumerating network state using the private network statistics framework. So traditionally, you would use these proc APIs that would allow you to enumerate open file handles. You could then, from those file handles, figure out which ones were network sockets, blah, 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 blah. It worked. It wasn't ideal. It also did not give us usage statistics. Like, I want to know for a given network connection how much data it's downloaded and uploaded, right? Because there might be some malware on your box that's exfiltrating large amounts of files every evening or midnight. That's something I want to know to classify this network traffic as perhaps suspicious. So turns out there's a utility called nettop. I don't know if any of you are familiar with it. I am not. If you pop a terminal on your Mac and execute nettop, it will give you a nice global list of all network activity on your system. Now, it does it as a snapshot. They run it kind of every few seconds, so it looks like it's continually updated, but in the background, they're just performing a snapshot. But again, it's great. So as we can see on the slide, we can see network activity based or tied to GitHub Desktop. And then also there's this weird Python connection on port 1337, which is the dummy malware we talked about earlier. So NetTop is great. It gives us a global snapshot of network connections, open sockets, et cetera, et cetera. It also gives us the bytes up and down for each connection, as well as basically all the information we would ever want about the connection, including the responsible process. That is, the process that is generating the network activity. Now, the problem is NetTop is closed source. So we wanted to write security tools that would mimic this. And so the way you do that is by, well, reverse engineering. If we use OTool, which is a utility that shows us what libraries a utility product application has dependencies on, we can see that it's linked against the network statistics framework, which is in Apple's private framework directory. We can then reverse engineer this, and actually the noted security researcher Jonathan Levin had already done this and created a open source command line version of NetTop that he called creatively NetBot. I took this a step further, built atop his research, and created a free open source utility called Netiquette. Netiquette is kind of like Activity Monitor, but for network activity on your system. So it's an application you run, and it provides a nice snapshot of network activity. And since it's a UI, it provides things like filtering. There's a checkbox that says ignore Apple processes. So it'll just show you any third-party network activity that's going, et cetera, et cetera. And again, it's fully free, fully open source. The idea was to create a utility for users, but also make the source code available so that people could see how it works, but also then perhaps write their own tools as well. So this is some of the code. There's several slides in this presentation that contain code. I don't want to walk through them in detail. That's probably somewhat boring to you, somewhat boring to me. But the goal is to have these snippets on the slide. So after this presentation, if you're interested in writing your own tools, which hopefully you are, you can go back and say, oh yeah, here's some snippets of source code that you can refer to. So here's an example of talking to the network statistics framework. In about 3 or 4 steps, we can pretty easily get all the information about network activity on a macOS system. We create what is known as a network statistics manager. We then tell it we're interested in all UDP and TCP traffic. And then we start what is known as a query, which is where the framework will go out and start enumerating all the network activity. And for each network entity, for example, a connection or open socket, it will then invoke our callback, which will allow us to programmatically do whatever we want with that information. So once we have this code, we can link in the private network statistics framework. There's nothing preventing us from using network private frameworks as long as we know what APIs to call and what parameters they expect, which we find out, as I mentioned, via reverse engineering. And then we compile and we run this. And as we can see on the slide, this is the information for one connection. It's a little hard to read, but that's almost by design on my part, because I really just wanted to show you how much information programmatically we are given even for just one connection. So this is for GitHub Desktop. It's talking to GitHub. And we get things obviously like the remote destination, the IP address it's connected to, the port. We also get the protocol. But we also then get the number of bytes up and down and all sorts of information. So this is great because this means if any malware is accessing the network, we will get all the information we could ever want about its connection. Now, there's one side to this approach, and it's still a great approach, so don't take this downside as like throwing the baby out with the bathwater. But it's an important caveat to point out, and that is since it's a snapshot-based approach, this means that if malware is not currently active on the system accessing the network, well, your snapshot's not going to show anything. So there are some examples of this. So we mentioned dummy. We can see in dummy's code that if it can't talk to its command and control server, it sleeps for 5 seconds. 3CX is another example. Once it generates a beacon interval, which is somewhat dynamic, this beacon interval will either be between 1 and 2 hours, which again means that if you perform the snapshot using the network statistics framework that we just talked about, and the malware is either sleeping or not connecting out, you won't see anything. So this is a little problematic, and what it means is we need to, or probably should, move to an approach that's more comprehensive. And that approach is network monitoring. So let's now talk about network monitoring, first starting by looking at how to build a DNS monitor for macOS. Now, the reason I thought this would be a good idea is because the vast majority of anything accessing the network, legitimate programs, but also malware as well, the first thing it's going to do is attempt to resolve the domain, for example, of its command and control server that it wants to connect to. And what will this mean? This will mean that DNS traffic will be generated. We talked about the 3CX example. This is a perfect example to drive home this point. The very first thing the malicious code did when it tried to connect out was to resolve the attacker's domain, which would generate a DNS request. So the idea is, instead of monitoring all network traffic, which we can do, and we'll show that in a minute, perhaps we can just focus on DNS traffic, which is perhaps more efficient, but still gives us the ability to efficiently both detect and potentially thwart any malware that's on the system. So you might be thinking, great idea. How do I do it? Well, let's look into that. So if you're going to be writing network monitoring tools on macOS and iOS as well, you're going to be using what is known as the Network Extension Framework. This is something that Apple introduced relatively recently. It's actually decent, now that they got the kernel bugs taken care of. So first off, it's fairly well documented. And also in WWDC, where they introduced it a few years ago, they actually have a whole developer video describing exactly how to use it. So this is really, really great. And if we look at the uses of the network extension framework, one of the things it does is it allows us to create what are known as on-device content filters or DNS proxy, essentially, monitors, which is exactly what we're trying to do. So reading the documentation for the network extension framework, we find a class named NEDNS Proxy Manager. And if we look at the very succinct documentation, it says this allows you to proxy all DNS traffic on a host, which for DNS Monitor is exactly what we want to do. Now, I'm somewhat lazy in the fact that if someone else has already done this, I don't want to redo it. And so I do what most programmers do. We hop on Google, where's the code for this? So I did this, and it was funny because other than Apple's brief documentation, the second hit was someone else saying, hey, has anyone done this? And there was this Stack Overflow post saying hey, this looks really cool. Has anyone done this? And the answer at the time was no. So I thought, OK, this is something I'm interested in as well. This seems like a powerful capability to have. Unfortunately, it doesn't look like there's a public implementation. So I should build an open source DNS monitor, both as a learning experience for myself, but then also, sharing is caring, make it open source. So the tool I wrote is called DNS Monitor, and as its very creative name implies, it will monitor DNS traffic on a macOS host. Again, free, open source. You can grab it from that URL. And when we run it, you can see that when I do a DNS query via something like NSLOOKUP, the DNS monitor, which is running from the terminal, will intercept that and, in this case, just print it out to the terminal. Now, you might be thinking, OK, this is great. How do I build a DNS monitor? And we're going to walk through that at a high level. But before we do that, I will warn you that Apple, unfortunately, has given us many, many prerequisites that have to be fulfilled before you can create a network monitor that you can deploy to other macOS systems. Now, I think the intention is monitoring network traffic has some privacy implications, so they don't want malware to be doing it. But as we'll see, they make you jump through an absurd number of hoops. So first off, you have to have a developer profile with the necessary entitlements, which means you have to pay them $99, go through and specify exactly what you want to build. You then also have to build your application, which has the DNS monitor, in a very specific way, and then sign and get Apple to notarize it. Now, you have built your lovely, you're laughing, this is good. I cry when I see this. So let's take Patrick, right? He's built a DNS monitor. He's paid Apple $99. He's got all the entitlements. He's solved all the kernel panics in Apple's code. He waited to get that patch. He's got it signed and notarized. He puts it on his website and tells all his users, hey, there's a free DNS monitor. Y'all should give this a whirl. The users are like, cool, we love this. What do we have to do? OK, you got to go to the website. And when you click download, you got to tell Safari, yes, I will allow this website to download something. Then when they double click it, Gatekeeper is going to pop up and say, hey, even though this is notarized and signed, meaning Apple has vetted it for malware, please confirm. So the user clicks confirm. Then the DNS monitor uses a network extension, which we'll talk about shortly. So Apple says, hey, even though this is signed and notarized, we block the extension. You have to go, as a user, manually approve that. OK, fine. So the user opens security and privacy, clicks allow. They then have to authenticate. And even after this, there's one more prompt saying, yo, are you sure? And then the user has to click allow again. And I say at this point, macOS is basically Windows Vista, because you might remember back in the day when Vista came out, Apple made these creative ads making fun of Vista for all its pop-ups, which I thought at the time was creative. But Apple, unfortunately, has become Vista. And I actually found a copy of this commercial, which we are going to watch. And it's going to require some audience participation. Just count how many times that Windows requires an authentication, recalling that on the previous slide, macOS asked for 6. So I don't know if the audio is going to work, but there's also a subtitle. So here we go.
Hello, I'm a Mac. Mac has issued a salutation, cancel or allow.
Allow, and I'm a PC.
You're returning Mac salutation, cancel or allow?
Allow.
Okay, what gives? Mac is asking a question, cancel or allow?
Allow. He's part of Vista, my new operating system. PCs have a lot of security problems, so he asked me to authorize pretty much anything I do.
You're pointing out Vista's flaws, cancel or allow?
Allow. I could turn him off, but then he wouldn't give me any warnings at all, and that would defeat the purpose, so.
You are coming to a sad realization, cancel or allow?
Allow.
So, not to pick on Apple too much, it was a very, very creative commercial, and macOS, we all kind of love it. But unfortunately, we see because of the autonomy that teams at Apple have, they don't really talk to each other. So each of them say, hey, a user should approve this one specific action, which seems good. But then when you string them all together, there's no communication between those. And then the user is left with clicking countless prompts, which, in my opinion, is problematic. All right, we're not here to knock Apple too much. Hopefully they're listening and do something about this. But let's get back to how we're going to write a system extension which contains the code to actually do the network monitoring. And again, there's a lot of code here. I'm not going to spend too much time on this. But basically, what you do is you create something known as a request to activate or load the system extension. You set a delegate, and then you submit a request to the operating system. And this is one of the things that triggers the prompt that the users have to allow. Now, once the system extension is running, we have to activate the network extension part of that. And again, we do this through a decent number of steps in code, which again is all basically telling the operating system, yo, please allow us to activate or kick off our logic that's going to be, in this case, proxying DNS packets so that we can examine DNS data. So behind the scenes, once we all do this, what macOS does is it takes the extension, which is in your application bundle, copies it to a root-owned directory, verifies that it's still signed and notarized and hasn't been tampered, and then executes it as a separate process running with root privileges. Because again, since it's monitoring network traffic, it needs to be running as root. And this is one of the reasons when you build a network extension, you have to put it in your application's system extension bundle, because this is how macOS finds it at load time. OK, we want to now talk about how to handle DNS traffic. And so again, we have to set up our extension in a specific way, which basically involves telling the operating system what class will implement the methods that the framework will invoke anytime a new DNS packet comes to us. So these are the delegate methods. A delegate method is basically something that the operating system or the framework will call. And if you implement it, it will be automatically invoked. So we have start and stop methods. These are just invoked when your extension is started or stopped. The most important one is handle new flow. And this will be automatically invoked by the framework anytime a new DNS request is generated by any program, any application, including malware, on the macOS system. So what we're going to do is handle this flow. Now, because the way the framework is set up, we're essentially a proxy. This means that even if we just perhaps want to monitor the activity, perhaps log the packets, we actually are responsible for sending them on to the DNS server. So we're basically, in a sense, man in the middling or person in the middling the connection, which means we actually have to take several steps, including opening the local flow, reading the request, and then sending it out to the DNS server ourselves. On the flip side, when the response comes back to us, we're responsible then for passing that back into the framework so it can be delivered back to the application that originally generated the DNS request. Now, getting raw DNS packets is great, but we want to start examining them, saying what domain are you trying to talk to? Or when the response comes back, okay, what domain did that match to? Because perhaps if those are known malicious domains or domains we don't trust, we want to block that. So we actually need to parse the DNS packets. Luckily, there is a library that ships with macOS that we can leverage. It's called libresolve, and it has a very helpful function that, given a raw DNS packet, will parse it for you. Definitely use this. Don't try to parse DNS packets yourself. It's painful. You'll probably introduce security bugs. Leave it to the experts. Now, at the beginning of this presentation, I said one of the main reasons that host-based network monitoring is the shit, I don't know if I can say that RSA, is awesome, is that, you can bleep that out, is that it allows us to identify the responsible process, which is super beneficial. But we haven't actually talked about how we do that. So we talked about this handle new flow method that's automatically invoked once we're up and running as a network extension, anytime, in this case, a DNS request or response comes out of the system or back into the system. And this method is invoked with a flow object, which is just an encapsulation about the connection. One of the class instance variables of the flow is an audit token. And an audit token is just a more secure and more modern way to identify processes. PIDs, or process identifiers, are often reused, so there's a whole bunch of race conditions involved with that. So what Apple has done is introduced audit tokens. So the great thing is, for this flow, we are given the audit token of the responsible process. And with the audit token, we can get its process ID, its path, its code signing information, everything we want about it. So this is how we securely and efficiently detect who is making the DNS request, or where the response should be delivered to. So if we add all this code into the DNS monitoring tool, compile it, and click through all the prompts, and run it, we can now see that if we execute an infected version of the 3CX application, that recall was surreptitiously modified by the North Koreans in the supply chain attack, we can see that the utility accurately identifies the responsible process, in this case the 3CX application, and we can see that the initial DNS request was, yes, routed through our network extension. We are now parsing it out and extracting the domain that it's trying to talk to. Now, it's important to understand that this request has not yet gone out. This is all still on the host. The operating system has basically given it to us first, which means we can decide to block it if we want. So imagine you have a block list or some other heuristics that allow you to classify DNS requests. Super easy to do. Basically, when you get the DNS request, you can examine what is known as the question. This is basically the domain that the DNS resolution will resolve to an IP address. And in this case, if that domain matches, for simplistic example here, something on a block list, you can just close out the connection and be like, yo, no, not cool. I don't want that to happen. If we do that, for example, if I put Google on the block list, if I then try to resolve google.com, either via NSLOOKUP or a browser, and I left this on accidentally, and then I was like, why is the browser not working? Well, this is why. The DNS monitor that we've written has detected that google.com should not be allowed to resolve, closes out the connection, which basically means that the resolution will fail and time out, effectively blocking the resolution. Now that's how we block the requests. Well, we might also want to block the response because perhaps the IP address that gets resolved is a known command and control server. Adversaries a lot of times will use different domains or register new domains, but oftentimes they will back to a known bad IP address. So the logic is pretty much the same. The request will come through our network extension, our DNS proxy, before being given back to the application. And with the answer, the IP address, we can examine that, and if it's on the block list or we don't like it for any other reason, we can simply, again, close out that connection, which will prevent it going back to the application that made that request. Now, you can also block these via creating what is known as an NX domain packet. This is just a different way to block a DNS request instead of closing out the connection, which does introduce a little bit of latency because it basically just triggers a timeout. So in this case, what we do here is, say we get a request that's going out. We don't want it to go out. We want to basically block it. What we do is we basically just make a copy of that request, and then we set some flags that say, OK, this is the response. And the response we create is known as an NX, or non-existent domain. This basically says what you're trying to resolve does not exist. There's no IP address for that. And then we allow that to propagate back to the application, which basically says, yo, resolution isn't a thing, isn't working. So just, again, another way to block that. Now, the last feature of this DNS monitor is the ability to dump the cache. This was one of the reasons I wanted to write it in the first place. I wanted to see like what domains have mapped to what IP addresses on my macOS system. I thought macOS would provide a way to do that. It does not. So the DNS monitor just registers its own cache. As requests and answers come, it just stores those. And at any time, you can send it a signal, and it will dump the mappings of all the domains and the IP addresses that were resolved to the terminal. Kind of neat. Now, I'm all about pointing out shortcomings. Nothing's ever a panacea, right? Nothing's ever a silver bullet. So in this case, a DNS monitor has the shortcoming of it only seeing DNS traffic, obviously, but still something that we should point out. So for example, back to Dummy, which connects out to a remote server to set up a remote shell, it uses a hard-coded IP address. Since it's a hard-coded IP address, exactly, no DNS traffic, which means our DNS monitor is not going to see anything. So the next step is to create a fully featured network monitor, which we'll briefly talk about in this point of the presentation. So the implementation for this is in another free open source utility I wrote called Lulu, which is a firewall. So it's basically a fully featured network monitor that also has rules built on top of it. And the idea is anytime anything tries to access the network on a macOS system where Lulu has been installed, if Lulu has not seen that before, it will alert the user and say, yo, something's accessing the network, right? This is a firewall. It's nothing super crazy. And if the user clicks allow, then subsequent connections that are tied back to that responsible application will be allowed. So how does this work? Under the hood, again, we're going to use the network extension framework. And instead of using that any DNS proxy provider, we're going to use another class, another object that this framework exposes to us, which is known as the NE filter data provider. And if we look at the comments from Apple's header file, which is where we find the documentation for all these lovely classes, we can basically see that it says all network traffic will be routed through anybody who implements this, and they will be given the opportunity to either allow or block it. So diagrammatically, pretty easy. We can either allow things based on the process or the traffic or user input. Again, standard firewall stuff. So let's briefly look at the code to implement this. Again, not going to walk through this. It's very similar to how we implemented a DNS monitor. Except in this case, there's a few other options where we can say, do we want to filter all packets, which means a full packet capture. In this case, we don't. We're only interested in the initial connection. So we say filter sockets equal yes. We then activate it, which essentially kicks it off. And in this case, again, it will invoke that handle new flow delegate method that we also saw in the DNS monitor. This implementation is a little different because it actually expects you to respond with either a allow or deny. And on the slide, you can see exactly how to do that. So if you're just wanting to perhaps passively monitor all network traffic, you would always return this allow verdict. But likely you want to apply some rules and maybe block certain unauthorized processes. OK, so to wrap this up, we need to now talk about heuristics. At this point, we have the ability to take snapshots of network traffic, monitor DNS requests and responses, or monitor all network traffic to begin with. But the question we haven't answered is, OK, cool, how do we classify that as either benign or malicious? Because it goes without saying that the vast, vast majority of legitimate software on your macOS system or iOS device is also going to access the network. So at this point, we'll be able to see that, but we need to classify whether it's benign or malicious. And there's basically two approaches to this. The first, and we'll dig into this more, is using that responsible process. And again, this is the main benefit of a host-based approach versus a network appliance that's plugged in somewhere into your enterprise. But we can still utilize network information from that request because we can see, for example, what domain it's trying to go to, what protocol, what port, et cetera, et cetera. And then we can apply what I would say are well-known approaches to classify that network traffic as suspicious or not. And these are well established. I'm sure there's many talks about this. But perhaps if there's a listening socket on a strange port, that's something you might want to investigate further. Endpoint, right? If it's talking to a known North Korean command and control server, you probably want to block that. Statistics, right? If every midnight it's exfiltrating gigs of data, again, you might want to take a look at that. So you can do a lot of classification based on the network information. I'm not going to dig into that because, as I mentioned, that's, in my opinion, well studied, well covered. So let's talk about, though, how, via the responsible process, we can determine fairly accurately whether the process and its network activity should be allowed, or if it's potentially malicious, are there red flags? Is this something that should be investigated further? And so some examples of things we can look for are we can see if the responsible process is not notarized. Now, I did pick on Apple earlier for inadvertently notarizing the 3CX infected installer. But the reality is the vast majority of macOS malware is not notarized, because to get it notarized, you basically have to send it to Apple, who check it, and most malware authors are not willing to take that risk. Whereas the vast, vast majority of legitimate software is notarized. So this is a pretty good heuristic if we can say, hey, is the process that's accessing the network notarized or not? We also might want to see if it's persistently installed or if there's an unusual process hierarchy. So let's take a quick look at these before we wrap them up. So recall that when a network flow is delivered to us, either if we're a DNS proxy or the network snapshot, we have a PID or an audit token. And from that, we can identify the responsible process. Once we have a PID or an audit token or a path, we can use Apple's code signing APIs to query that process to get answers like, is it notarized? Is it signed? Et cetera, et cetera. So this is how you do that. I've implemented this in one of my other free open source tools that will block notarized programs. But the idea is you basically use the code signing APIs, and Apple will say yes or no. We also might want to check if the process that's accessing the network that we don't recognize is persisted or not. In the context of this presentation, persistence means that it has installed itself in a manner that every time the operating system is restarted, for example, the system is rebooted or the user logs in, it will be automatically re-executed. This is something the vast, vast, vast majority of software, malware specifically, tries to gain, because if malware doesn't persist and you reboot your system, you basically disinfected yourself. So if you see something accessing the network, you might want to say, OK, I don't recognize this. Is it also persistent? And if so, that's another red flag that might be indicative of the fact that it's malware or not. So on recent versions of macOS, Apple has introduced what is known as background task management. And background task management is a mechanism that governs all persistence items. Unfortunately, it's proprietary and undocumented. Thanks, Apple. But I reverse engineered it, and I created a free open source utility that can parse and deserialize this database and show you basically everything that's persisted on your macOS system. So dump BTM can do that. And here, for example, we see an item called com.startup.plist, which turns out to be how the malware authors of Dummy persisted. Now, the last thing I want to talk about as a heuristic is detecting strange process hierarchies. So if you remember many slides back when we were talking about network snapshots, we saw GitHub Desktop and then also Python that had a connection to an IP address on port 1337. Now, Python itself is a platform binary, meaning it generally ships with Mac OS. So like, Python itself is not malware. Of course, malware authors could abuse it. So how do we determine if Python is being used in a suspicious manner? The answer is process hierarchies. So if we install Dummy and allow it to execute, we will see a network connection originating from Python. We can say, OK, that's strange, but we don't have enough information about that. Is that just a developer Python script? Or is it a persistent Python script that's also malware? What we can do is we can look at the process hierarchy. And in this case, we will see that Python has been executed by bash, which has been executed by launchd, meaning it's persistent. So now we have like a persistent Python script that's connecting out to a port on 1337. Like, that's enough red flags for you to be like, OK, I should really take a closer look on that. OK, we made it. Conclusions and takeaways. The big takeaway is, I believe that, and hopefully I've convinced you all as well, that we can leverage macOS's networking frameworks to heuristically detect malware. And this is based on the very obvious observation that the vast majority of malware is going to access the network. And therefore, if we can have mechanisms, approaches, software, extensions, et cetera, that can detect and classify this activity as unauthorized, we should be able to generically detect malware, even malware that other detection mechanisms have failed to detect. I briefly want to thank the companies and products that support the Objective-C Foundation. It's a nonprofit. Wouldn't be able to do all the awesome research and free open source tools without them. So brief thanks to them. And then I do also want to mention that right after this talk, I will be going over to the RSA bookstore to sign some books. So if you want to pick up an awesome book on Mac malware analysis, come check it. All proceeds from that go back to the foundation. We can also talk more about this. And then tomorrow at Jamf's booth, I will be doing a fireside chat about macOS malware. As you can tell, I'm very passionate about this. So if you want to chat more, come see me at the bookstore or not. I believe we have 2 minutes, 1 minute for questions. So if there's any questions, I will take those now. Like I said, right after this, I'll be outside. We can chat as long as you want. We can head over to the book signing, whatever. But yeah, any questions? Awesome. That means you understood everything perfectly. I really appreciate it. I do want to thank you again for attending this very technical talk. I know it didn't have AI in the name, but so I appreciate you showing up. Also, RSA sends a little survey around. Any constructive criticism is always very much appreciated. So thank you so much again, and enjoy the rest of the conference.